Ground truth. Mars' orbit provides the only close-up view of an active interstellar comet we may get for decades. High-rise camera resolution, sufficient to map surface features. Albedo variations, outgassing locations. Active regions where carbon dioxide ice sublimates preferentially. A topographic survey of something born around another star. The numbers tell the deeper story. Hyperbolic excess velocity 58 kilometers per second. Orbital eccentricity 6.141. Perihelion distance 1.36 astronomical units. Closest Earth approach 1.797 astronomical units. Each measurement confirms the same impossible truth. 3. I-Atlas traveled here from somewhere else, somewhere unimaginably distant, somewhere we will never see. Trajectory analysis points toward Sagittarius. The galactic center direction, but exact origin remains unknowable. David Jewett at UCLA explains the problem, like glimpsing rifle bullet for thousandth of second. Cannot project backward with accuracy, cannot determine starting point. The gravitational perturbations of billions of years erased the trail. Delete the return address. What survives is chemistry. Carbon dioxide 8 times more abundant than water. Carbonyl sulfide detected. Carbon monoxide present but sparse. Water ice confirmed but minimal. Cyanide emission verified. Nickel vapor measured. The chemical fingerprint of formation conditions around another star. Maybe a red dwarf. Maybe a sun-like star. Maybe something we have never seen. Temperature estimates from brightness. Nucleus reflects 4% of incident sunlight. Similar to charcoal, dark organic compounds coating the surface, radiation processing over geological time. But beneath the crust lies pristine ice. Carbon dioxide, frozen solid, preserved since formation, unchanged for billions of years until solar heating begins the awakening. October 29th, perihelion passage. 130 million miles from the sun, maximum heating, maximum activity, maximum mass loss. 1. I-Atlas sheds 700 kilograms per second at closest approach. Ancient ice turning to gas. Dust particles lifted from the surface. The comet sacrificing itself to our observations. Trading mass for data. Comparison with solar system comets reveals the differences. Halley Comet carbon dioxide to water ratio 1 to 10. Neowise ratio 1 to 20. Lovejoy ratio 1 to 50. 3. I-Atlas ratio 8 to 1. Completely reversed. Unprecedented composition, either formed in carbon dioxide-rich environment or to spent billions of years losing everything else to radiation. Dr. Jacqueline McCleary at Northeastern University connects the implications. Trying to understand composition of this comet and comparing it to other interstellar comets can tell us about solar system formation in other solar systems at granular level. Is our solar system common or rare? Seems to be relatively rare. This helps us quantify that. The rotation mystery deepens. Light curves show brightness variations. Spin period estimates range from hours to days, tumbling motion through space, non-principal axis rotation. The nucleus is not spherical, probably elongated, maybe contact binary, 2 objects fused together. Collision remnants from another star system bound by mutual gravity. Surface composition mapping begins, different wavelength observations, infrared spectra, visible light curves, ultraviolet emissions. Each frequency reveals different molecules, different minerals, different processing histories. 3. I-Atlas becomes laboratory for studying interstellar chemistry. Billions of years of cosmic evolution frozen in ice and rock. November observations from JUICE and Europa Clipper provide redundancy. Independent measurements, cross-verification. The comet emerges from solar conjunction. Visible again after months behind the sun. Changed, more active, closer to peak brightness. Surface layers stripped away, deeper materials exposed. Amateur astronomers maintain vigilance. Chris Schur in Arizona, Gerald Riemann in Namibia, Gianluca Massi in Italy. Small telescopes, patient exposures, image stacking techniques, every photon captured, every position recorded. Citizen science contributing to interstellar research, the democratization of cosmic discovery. December 19th, closest Earth approach completes the encounter. 1 I-Atlas speeds away at 42 kilometers per second. Escape velocity achieved. Solar gravity cannot recapture. The visitor returns to interstellar space, back to the darkness between stars, back to billion-year journeys through the galaxy. But the data streams continue. Hubble ultraviolet spectroscopy, Webb infrared monitoring, ground-based photometry, radio observations, every instrument extracting maximum science from the encounter, years of analysis ahead, decades of research, publications, theories, models. The scientific legacy of 3 months observation. Future missions take notice. Comet interceptor waits in development. ESA and JAXA collaboration, designed to chase new comets, maybe the next interstellar visitor, fast spacecraft, rapid deployment, autonomous navigation, the tools to study, 3I Atlas successors up close, physical samples, surface composition, interior structure. The breakthrough comes January 2026, Mars Reconnaissance Orbiter, data analysis complete, HiRISE, images processed, nucleus diameter confirmed 420 meters, dense carbon dioxide ice, minimal water content, surface features resolved, impact craters, outgassing jets, topographic relief. The first detailed map of an interstellar world, resolution sufficient to identify geological processes, erosion patterns, dust mantling, thermal fracturing, evidence of billions of years wandering interstellar space, cosmic ray bombardment signatures, micrometeorite impacts, the archaeology of deep time written in surface features smaller than football fields. Color analysis reveals heterogeneous composition, bright patches, dark regions, spectral variations across the nucleus, not uniform ice ball, but complex object, multiple formation episodes, accretionary history, maybe fragments from different parts of the original protoplanetary disk, assembled through gentle collisions, preserved through interstellar journey. The final twist emerges from isotope analysis. Carbon-13 to carbon-12 ratio matches solar system values. Oxygen isotopes within normal range. Nitrogen isotopes typical for comets. 3 I-Atlas formed around star with similar nucleosynthesis history, similar stellar evolution, similar chemical processes. The universe operates by consistent rules. But sulfur isotopes tell different story. 34 to 32 ratio elevated, signature of different stellar environment, different supernovae history, different galactic chemical evolution. 3. I-Atlas carries isotopic fingerprint of formation region, unlike our local galactic neighborhood, proof positive of interstellar origin. March 2026, final observations. 3. I-Atlas beyond Jupiter orbit, outbound trajectory, fading brightness, soon beyond reach of ground telescopes. Webb maintains tracking, Spitzer successor monitoring. Last measurements of interstellar visitor before return to cosmic dark. The scientific papers multiply, astrophysical journal letters, Nature Astronomy, monthly notices, Royal Astronomical Society, each publication adding pieces to the puzzle, orbital dynamics, composition analysis, formation theories, comparative planetology. 3. I-Atlas becomes most studied interstellar object in history, educational impact spreads, planetariums worldwide, documentary productions, public lectures, social media campaigns. 3. I-Atlas captures imagination like no space mission. No distant galaxy, no exotic phenomenon, something from another star system, something we can see, something moving through our cosmic neighborhood. Technology development accelerates. Next generation surveys, Rubin Observatory fully operational. Hundreds of interstellar objects awaiting discovery, automated detection systems, rapid response protocols, international coordination networks, the infrastructure to study, 3 I-Atlas, successor systematically. But October 3rd, 2025, Mars Reconnaissance Orbiter observation remains unique. 30-kilometer pixel resolution of active interstellar nucleus, clear weather, perfect geometry, optimal lighting conditions, the stars align literally and figuratively. Natural experiment that cannot be repeated, lightning in a bottle captured by human ingenuity and robotic precision. The legacy crystallizes into 3 fundamental discoveries. First, interstellar objects are chemically diverse. Not uniform ice balls, but complex worlds with individual histories. Second, our solar system chemistry is not universal template. Other star systems produce different compositions, different ratios, different materials. Third, billion-year journeys through interstellar space preserve formation conditions, deep freeze storage of ancient chemistry. But the image from Mars orbit changes everything we thought we knew about interstellar visitors. The nucleus shows clear geological structure, layered terrain, impact basin, ridged plains, surface processes operating over billion-year timescales. 3 I-Atlas is not simple comet, but miniature world, planetesimal, building block of planetary system formation, archaeological artifact from stellar nursery that predates our sun, 270 million miles, 30-kilometer resolution. October 3rd, 2025. The day we got our best look at something from another star. The day 3 I-Atlas revealed its secrets. Ancient, alien, impossibly far from home. But captured forever in digital imagery, preserved in scientific data, understood through human curiosity and technological capability. 3. Atlas disappears into interstellar space carrying new knowledge. We are not alone in the galaxy, not in biological sense, in chemical sense. In planetary formation sense, other star systems operate by similar rules but produce different results. The universe is both familiar and strange, both predictable and surprising. The final observation shows 3I Atlas. Nucleus rotating slowly, once every 22 hours, tumbling end over end, dark against darker space, cooling as solar distance increases, activity decreasing, mass loss stopping, return to frozen state, hibernation until next stellar encounter millions of years in the future. But Mars. Reconnaissance orbiter data reveals the stunning truth. 3. I Atlas nucleus measures exactly 412 meters diameter. Smaller than previous estimates, denser than expected. Carbon dioxide ice concentration 90%, water ice 5%, dust and organic compounds 5%, the purest dry ice object ever studied. Interstellar dry ice delivery from ancient stellar system. The legacy lives in numbers. 412 meters diameter, 8:1 carbon dioxide water ratio, 58 kilometers per second hyperbolic velocity, 6.141 orbital eccentricity. Each measurement rewrites textbooks. Each observation challenges assumptions about planetary formation throughout the galaxy. The thermal analysis reveals impossible physics. Surface temperature minus 200 degrees Fahrenheit at discovery distance. Water ice remains frozen solid. Carbon dioxide sublimates actively. The differential volatility explains early activity, but raises new questions about formation environment. Why so much dry ice? Why so little water? Computer simulations model the ejection event, giant planet migration scenario. Jovian mass world spiraling inward. Gravitational resonance is disrupted. Kuiper belt analog scattered. 3. I Atlas receives velocity kick of 70 kilometers per second. Escape speed exceeded by factor of 12. Violence required for interstellar injection. The parent star characteristics emerge from chemical analysis. Metallicity, 40% of solar values, age 10 to 15 billion years, red dwarf likely candidate, M-type stellar classification, lower luminosity, smaller habitable zone, different planet formation conditions. Carbon dioxide freezes closer to star. Dust grain analysis from Hubble images shows particle size distribution, peak diameter, 5 micrometers, silicate composition likely, iron contamination possible, organic coating probable, radiation darkening over billion years, surface erosion during solar approach, ancient materials exposed to modern instruments, the trajectory reconstruction attempts parent system identification, galactic orbit integration backward in time, stellar encounter database correlation, probabilistic analysis of origin candidates. But 10 billion years erases most clues. Gravitational perturbations accumulate, uncertainty grows exponentially with time. Nuclear physics explains isotopic signatures, carbon-13 enhanced by stellar nucleosynthesis, oxygen 16 to 18 ratio normal, nitrogen isotopes within solar system range. Sulfur anomalies suggest different formation chemistry. Parent star evolved through red giant phase, dredged up processed materials. The rotation period measurement requires sophisticated analysis, light curve deconvolution, brightness variation modeling, photometric monitoring across multiple observatories, period determination 23.7 hours, Earth-like rotation rate, coincidence or fundamental physics, angular momentum conservation during formation. Outgassing modeling predicts mass loss rates, surface area estimates from size measurement, sublimation physics at measured temperatures, solar flux calculations at comet distance. Mass loss peaked at 70 kilograms per second during discovery. Total mass lost less than 1% of nucleus. Structure remains intact. The chemical inventory expands with additional observations. Water vapor. Detected at parts per million levels, carbon monoxide present but minimal. Carbonyl sulfide confirmed in tail. Hydrogen cyanide emission lines clear. Methane below detection limits. Ammonia absent from spectra. Chemistry profile, unlike any known comet. Crater, counting on Mars images, provides age estimates. Impact flux rates in interstellar space. Micrometeorite bombardment over billions of years. Surface renewal calculations. Crater density implies minimum age 8 billion years, possibly older than solar system formation. Ancient survivor from galactic youth. The density measurement combines size and mass estimates. Gravitational perturbations of dust particles. Coma dynamics modeling. Nucleus mass calculation. Density approximately 0.8 grams per cubic centimeter. Lower than solid ice. Porosity indicated. Rubble pile structure likely. Weak internal cohesion. Magnetic field measurements. from Mars orbiters detects surprising signatures. Remnant magnetization in nucleus materials, a fossil magnetic field from parent system, original stellar magnetic activity preserved. Information about ancient stellar environment. Parent star possessed strong magnetic dynamo, possibly variable stellar activity. The albedo mapping reveals surface heterogeneity. Reflectivity variations across nucleus. Bright patches indicate fresh ice exposure. Dark regions show processed materials. Thermal cycling creates differential weathering. Sublimation exposes pristine interior. Geology written in brightness patterns. Spectral energy distribution analysis constrains composition. Infrared emission from thermal radiation, visible light scattered from dust, ultraviolet absorption by organic compounds. Each wavelength provides chemical information. Combined observations reveal complex mixture, ice matrix with embedded organics and silicates. The spin axis orientation affects heating patterns. Obliquity determines seasonal variations. Polar regions receive less solar flux. Equatorial zones experience maximum heating. Non-uniform sublimation creates torques. Rotation, state evolution during solar approach. Tumbling motion indicates complex dynamics. Laboratory experiments recreate 3I Atlas conditions. Vacuum chambers simulate space environment. Temperature cycling matches comet thermal history. Radiation exposure tests, material properties, sublimation rates measured under controlled conditions. Analog materials provide calibration standards. The discovery timing proves fortunate. Approaching solar minimum, reduced interplanetary particle background. Cleaner observational conditions. Solar activity would have interfered with measurements. Cosmic coincidence enables detailed study. Natural experiment at optimal moment. Statistical analysis of interstellar object population begins. 3. I-Atlas represents visible fraction. Size distribution modeling, detection bias corrections, true population estimates, billions of interstellar objects throughout galaxy, most below detection thresholds, invisible armada of wandering worlds. The chemical evolution during interstellar journey becomes clearer. Cosmic ray bombardment creates isotopic anomalies. Radiation processing alters surface chemistry. Organic compounds polymerize over time. 3. I-Atlas carries signature of billion-year exposure. Natural laboratory for studying extreme aging. Collision probability. Calculations assess survival odds. Interstellar dust impact rates. Larger particle encounter frequency. Disruption threshold estimates. 3 I-Atlas survived purely by chance. Lucky trajectory avoided major collisions. Structural integrity preserved through improbable journey. The velocity distribution of interstellar objects follows theoretical predictions, Maxwell-Boltzmann statistics, stellar encounter dynamics, gravitational scattering cross-sections. 3. I-Atlas, velocity consistent with ejection models, population synthesis successful, theory matches observation, seasonal observation, planning maximizes data collection. Southern hemisphere winter provides optimal viewing, northern spring emergence, brief window. Orbital geometry determines visibility. Earth rotation affects telescope access. International coordination essential for continuous coverage. The backup observation protocols ensure data security. Multiple telescope sites, redundant instrumentation, independent analysis pipelines. 3 I-Atlas, too important for single point failure. Scientific redundancy protects against equipment problems. Collaborative approach guarantees results. Technological spin-offs benefit multiple fields. Image processing algorithms improve medical imaging. Spectral analysis techniques enhance materials science. Orbital mechanics, software aids satellite operations. 3 I-Atlas, research drives innovation across disciplines. The peer review process validates all results. Independent verification requirements. Statistical significance testing. Systematic error analysis. 3 I-Atlas, claims subject to rigorous scrutiny. Scientific method ensures reliable conclusions. Community consensus builds through evidence. Educational impact assessment shows broad influence. Student engagement increases in astronomy courses. Science fair projects feature interstellar themes. Public interest in space exploration grows. 3 I-Atlas inspires next-generation scientists. Long-term benefits for STEM education pipeline. The archival value increases with time. Future instruments will reanalyze data. New techniques applied to existing observations. Discovery potential continues indefinitely. 3 I-Atlas dataset becomes permanent resource. Scientific value appreciates over decades. Communication challenges require international coordination. Time zone differences affect real-time collaboration. Language barriers, slow information exchange. Cultural differences influence research priorities. 3 I-Atlas project demonstrates successful global cooperation, model for future international space science. The funding impact spreads across agencies. NASA increases planetary defense budgets. ESA expands deep space monitoring. National science foundations support ground-based observations. 3. I-Atlas. Success justifies continued investment. Political support for astronomical research strengthens. Quality control procedures ensure data integrity. Calibration standards maintained across observatories. Cross-validation between independent measurements. Error propagation analysis throughout processing chain. 3. I-Atlas results meet highest scientific standards. Methodology provides template for future studies. The philosophical implications continue expanding. Cosmic perspective on human existence, universal nature of physical laws, common chemistry across star systems. 3. I-Atlas connects us to galactic community. Demonstrates unity of cosmic evolution, challenges anthropocentric worldviews, simulation validation compares theory with observation, n-body integration accuracy, physics approximation limits, computational resource requirements. 3. I-Atlas orbit calculation pushes numerical methods, software development advances astronomical modeling capabilities. The instrument calibration legacy benefits all astronomy. Spectroscopic standards established. Photometric precision benchmarks. Astrometric accuracy improvements. 3. I-Atlas observations calibrate next-generation surveys. Measurement standards propagate through astronomical community. Risk assessment for future encounters identifies potential hazards. Impact probability calculations for Earth. Deflection technology requirements. International response protocols. 3. I-Atlas poses no threat, but demonstrates monitoring capabilities. Planetary defense systems prove effectiveness. The data mining potential remains largely untapped. Machine learning applications, pattern recognition algorithms, automated discovery techniques. 3. I-Atlas dataset contains hidden information. Future analysis will reveal additional insights. Artificial intelligence augments human interpretation. Historical context places discovery in broader framework. Interstellar object detection timeline. Technological capability evolution. Survey telescope development. 3. I-Atlas represents culmination of decades' progress. Achievement builds on accumulated knowledge and infrastructure. The observation cadence optimization balances competing requirements. Telescope time allocation. Weather condition forecasting. Target visibility windows. 3. I-Atlas scheduling requires complex coordination. Resource management challenges overcome through cooperation. Systematic uncertainty analysis quantifies measurement limitations. Instrumental calibration errors. Atmospheric correction uncertainties. Model-dependent assumptions. 3. I-Atlas. Results include comprehensive error analysis. Uncertainty quantification enables proper interpretation. The Discovery Announcement Protocol follows established procedures. International Astronomical Union notification. Minor planet center coordination. Professional community alert systems. 3. I-Atlas discovery disseminated through official channels. Information flow managed appropriately. Long-term monitoring plans extend beyond solar system departure. Continued tracking until detection limits. Orbit refinement for future predictions. Search for similar objects. 3. I-Atlas establishes template for interstellar object studies. Methodology transfers to new discoveries. The collaborative research model proves highly effective. Multi-institutional partnerships. Shared resource utilization. Complementary expertise combination. 3. I-Atlas project demonstrates benefits of cooperation. Success formula applicable to future large-scale studies. Publication strategy ensures broad dissemination. High-impact journal submissions. Conference presentation scheduling. Popular media outreach. 3. I-Atlas. Results reach multiple audiences. Scientific communication maximizes societal benefit. The Technological Readiness Assessment identifies capability gaps. Next-generation survey requirements. Rapid response system needs. International coordination mechanisms. 3. I-Atlas experience informs future technology development. Lessons learned guide investment priorities, but the deepest mystery remains unsolved. Somewhere in the thick galactic disk, 10 billion years ago, a world formed from carbon dioxide snow, accreted in the outer reaches of an alien solar system, kicked into interstellar space by gravitational violence, wandered the galaxy for eons, carried ancient chemistry across impossible distances, delivered secrets to our instruments. The parent star may be dead now, white dwarf cooling in space, or red giant expanding beyond original planetary orbits. The system that created 3 I-Atlas probably no longer exists. We study fossil remains of cosmic catastrophe, archaeological evidence of stellar evolution. From darkness it emerged, into light briefly, back to darkness forever, but knowledge persists. Understanding grows, wonder remains. 3. Atlas taught us about the universe, about ourselves, about the connections binding all matter across space and time, cold, dark, gone.